This is a lecture introducing the different types of chemical bonding, specifically ionic bonding and covalent bonding. All chemical bonds are the result of electrostatic attractions, which is simply the attraction between oppositely charged particles. So in a chemical bond, what we're talking about is the negatively charged electrons of one atom being attracted and held closer to the protons of another atom. The two primary types of chemical bonds are ionic versus covalent. They are both electrostatic attractions, as are all bonds. There is also a special interaction that occurs between metallic atoms, metal atoms, which we'll mention briefly, but we won't really go into. So you will occasionally encounter called metallic bonding, but we won't go into much detail on that. Even though we separate most of the chemical bonds into either covalent or ionic, there's not a clear-cut dividing line. As with so many things, we have a spectrum where we have pure covalent on one end and pure ionic on the next, and all the other bonds are somewhere in between. So our dividing line between covalent and ionic is somewhat arbitrary. So just to kind of give you a big picture, how do we distinguish ionic versus covalent bonds? Well, an ionic bond typically occurs between a metal and a nonmetal. So if you remember, the metals are located to the left of the stair step on the periodic table, and the nonmetals to the right of the stair step. Ionic bonds involve the complete transfer of valence electrons from one of the bonding atoms to another. And so you have a metal. Metals like to give up electrons to become cations. And so that's what happens. The metal atom donates one or more of its valence electrons to the nonmetal. The nonmetal accepts it, and so the metal ion becomes a cation, a positively charged ion. The nonmetal atom becomes an anion, a negatively charged ion. And table salt, sodium chloride, is a perfect example of that. Once you have the ions, the charged particles, obviously they're very strongly attracted to each other through these electrostatic attractions, and we have an ionic compound. Because of the strong attraction, ionic compounds are always crystalline solids, and again, you end up with like a three-dimensional just conglomerate of oppositely charged ions. So it's not like a molecule like water where you can draw out individual molecules that exist somewhat separately from each other. It's just a big connected lattice for ionic compounds. But we do take look at these lattices and pick out the simplest ratio, repeating ratio, of elements involved in it, and we call that a formula unit. So when you see formula unit, you can think molecule, but just realize it's not really a separate molecule. Molecule are what we call covalently bonded compounds. Alrighty, so that brings us to covalent bonds. Covalent bonds occur between two nonmetals, and rather than transferring their electrons, they share their valence electrons. And again, we call that the compound that two nonmetals make a molecule. Okay. Covalently bonded molecules can exist in the gas, liquid, or solid state. If you remember, we said that ionics are always solids. And just kind of as an aside, but a handy thing to know in chemistry, is that there are 7 elements that exist naturally in our world as what we call diatomic elements. So basically they exist as twins in nature. You will not see them like a hydrogen atom. You will not see it on its own naturally in our world. And we can go into the reasons later, but basically these elements, by sharing their valence electrons with each other, stabilize each other, and so that's how they prefer to exist. Now, just kind of as an aside, there are a couple more elements that exist in nature in more than a single atom. Phosphorus, the most stable form of phosphorus, is P4, four phosphorus atoms bonded together, and sulfur, the most stable form, is S8. Alrighty, so because, especially when we get to chemical reactions, it'll be handy to know those 7 diatomic elements. This is, I think, the coolest way to memorize them. If you look at a periodic table, the 7 elements, I'm just going to give you the little limerick you use to remember it. So hydrogen is element number 1, right? So start there. Skip over to element number 7 because there are 7 diatomics, and then draw a number 7. And you will automatically have your 7 diatomics, which is pretty cool. All right, so just kind of an overview reminder of the difference versus covalent versus ionic. Covalent, 2 nonmetals, ionic, a metal and a nonmetal. And covalent makes molecules, ionic makes, I left the name off here, formula units. You will see molecules represented in a number of different ways. The simplest way, the easiest way, is just the molecular formula, where you have element symbols combined with subscripts to tell you how many of each type of element are in the compound. Then we have structural formulas, which give you a little more information. They tell you whether the bond between 2 atoms is a single bond, double bond, triple bond, etc. And then we have the 3-dimensional models, which attempt to allow you to visualize how the molecule actually exists, what type of space it occupies. Probably the most accurate model is a space-filling model, because in reality, atoms are not individual little balls with sticks that attach them to other atoms. They are simply atoms that get as close as they can to each other to maximize the electrostatic attraction. All right, and briefly, we're about at the end of this PowerPoint, but I want to leave you with a concept of chemical formulas. So chemical formulas is just our shorthand way of writing the atoms that have bonded together to form different compounds. There are 2 types of formula. I'm going to skip down halfway down the page. Molecular formula is the actual formula that exists for a compound. C4H8 tells us that this compound has 4 carbons and 8 hydrogens. All right, so that's just the most common type of formula. But I do want you to be aware of an empirical formula. An empirical formula is just a mathematically simplified version of the molecular formula. So if the molecular formula is C4H8, just as you would in math, can you simplify this ratio of elements? Yes, you can divide both subscripts by 4. And what would we get then? Okay, we would get CH2. And that would be the empirical formula. Okay, so it's just a mathematically simplified version which tells us the simplest ratio of elements that exist in that compound. Why are we bothering you with an empirical formula? It turns out that because of the analysis equipment that chemists have, they quite often get their information in the form of an empirical formula and then have to get further information to figure out what the actual molecular formula is. And that's it for this introductory lecture on chemical bonds.